SwayamPrabha. Digital India. Educated India.
In today's lecture, we will discuss about composite laminates. So far we have seen the properties of composite plies or lamina. In the last lecture, we defined the properties with respect to the XY, which is a global system. Now, today we will discuss the properties of a laminate with respect to the global system, and we will see the relation between the stress resultants in the laminates with the strains. So, our composite laminate looks like this. It is made of several plies. One more ply. So, and then we know the properties of the individual plies. We know their stress strain relation with respect to their own fiber orientation direction and with respect to a global x y direction as well. So, now today we will integrate the quantities along the thickness of the ply thickness of the laminate, and we will relate the stress resultants in terms of the strain components, and the strains are already related to the displacement components. So, finally, it would relate the stress resultants with respect to the displacement components. Now, we have sigma x, sigma y and sigma s as our stress components. So, if we integrate this sigma x along the thickness, so z is the thickness direction. So, if we integrate the properties the sigma x along the thickness direction, that gives us our n x, which is normal force along x. If we integrate sigma y along thickness direction, that give us n y, which is normal force along y direction, and if we integrate sigma s along z, that gives us n s, which is shear force. And then if we multiply sigma x with minus z and integrate, that gives us a moment m x. Now, please understand this, if we integrate sigma x after multiplying with minus z along the z direction, the moment that we get is with respect to the y direction. So, this moment is acting with respect to y direction. So, it is a moment like this, it is a bending moment like this, it acts with respect to y direction, but still instead of calling it m y, we are calling it m x, just because we are getting it by integrating sigma x. Similarly, we get another quantity m y, and this also this acts with respect to x direction, but still because we are getting it by integrating sigma y, we are calling it m y. And we get a moment m s, which is a twisting moment in the x y plane. So, today we have to get these quantities and relate these quantities n x n y n s, m x m y m s with respect to the strain components, and accordingly this relation comes with respect to the displacement components as well. Now, before doing that, let us define a few things. So, let us look at the stack of plies as this. So, we are looking it just from one side. So, we get to see something like this. we have plies. So, this is layer 1, layer 2, we can call a generic layer as layer k, and then we have n number of layers. And we define the mid plane as our axis. So, we define z with respect to the mid plane. So, this can be x or y axis depending on from which direction we see it, and our z goes here. So, this point, the z coordinate of this point we call z0, the z coordinate of this point we call z1, z2, and this is the kth layer. So, here we have zk minus 1, here we have zk, here we have zn minus 1, here we have zn. So, we can say that the z coordinate of the junction between the k minus 1 and kth layer is zk minus 1, and the z coordinate of the junction between the kth and the k plus 1th layer is zk. Now, if we want to find our n, n vector. So, n vector is just a vector of nx, ny and ns. So, if you want to get that, we just have to integrate our sigma vector, and sigma is just this. So, this is sigma x, sigma y, sigma s. Now, this integration is from here to here along the entire thickness. So, what we will do is we will break the integration into different, we will break the integration into different plies. So, we will integrate over each ply and then sum it up. So, we can write this integration as k is equal to 1 to n z k minus 1 z k, because kth ply spans from z k minus 1 to z k, and then we integrate. Now, for the kth ply, we can write our stress as the Q matrix with respect to xy system for the kth ply multiplied by epsilon. This relation we already derived in the last lecture. Now, if we write the stress, if you write the strain displacement relation, we know that epsilon x is equal to del u by del 0 minus z into del 2 w by del x 2, and we call it epsilon x 0 minus kappa x, or let us put the 0 in the superscript as well. So, epsilon 0 x. Accordingly, we already know. So, we have our assumption is there is no shear deformation. So, as per this we can write epsilon y, which is normal strain along y direction in the same way, and that becomes epsilon 0 y minus kappa y. So, we are calling del 2 w by del x 2 as kappa x and del 2 w by del y 2 as kappa y. I have to multiply minus z, and accordingly we can write epsilon s equal to epsilon 0 by epsilon y plus del u 0 by del y plus del v 0 by del x minus twice z del 2 w by del x del y. So, this becomes epsilon 0 s minus z into 2 kappa s. So, we are calling twice del 2 w by del x del y as kappa s. So, this entire epsilon vector can be written as epsilon 0 minus z into kappa. So, epsilon 0 is a vector of epsilon 0 x, epsilon 0 y, epsilon 0 s, and kappa is a vector of kappa x, kappa y and kappa s. So, we can bring everything here and write k is equal to 1 to n. Within each layer we integrate from z k minus 1 to z k, and this can be written as multiplied by epsilon 0 minus z kappa, and this entire thing is integrated. So, these are the relations, strain displacement relations, using which we can write this. So, now we are integrating these q's over thickness and summing it up. Now, this epsilon 0 does not is independent of z. So, it can be taken out of the integral. So, these q's are integrated over the thickness and summed up. Similarly, here kappa is independent of z. So, it can be taken out. So, minus z q can be integrated over the thickness and can be summed up. So, finally, we can write a relation like this. Where our A is summation of k is equal to 1 to n of the integral of k from z k minus 1 to z k, and similarly we can define a quantity B, which is a similar integration, but the integrand is minus z multiplied by q. So, this is one relation. So, our n vector is equal to A epsilon plus B kappa. Now, we define another vector which is m, and m as we know is obtained by integrating minus z into stress. So, now we can write same thing minus z into stress, and this becomes minus z into q multiplied by epsilon 0 plus z square multiplied by q into kappa, and this entire thing is integrated and summed over. Again epsilon 0 goes out and we are left with minus z into q, and we know that if we integrate minus z into q and sum up, we get a quantity called b. We have already defined it. So, this is b into epsilon 0, and here we have z square q, its integration and its summation, and let us call this quantity as d. So, let us define d as z k is equal to 1 to n integral of z square q over z k minus 1 to z k. Now, we can always write this entire quantity in a more compact form as this. As this. So, this is how the stress resultants, which are forces and moments, are related to the strain components. Now, we can see that the certain parts of these matrices become 0, or there are certain relations that comes up between these parts of matrices depending on the lamination sequence. So, we will now see that. Okay. So, for example, we can see here that this B matrix relates the in plane force components with the out of plane displacements, because so these are the in plane force components, these are the bending moments. Here we have epsilon 0, it has u 0 and v 0 only. So, again it has in plane displacement components, and kappa has out of plane displacement, which is w. So, u v w are displacement along u v w are displacement along x, y and z, and u 0 v 0 are the mid plane displacement components, and w is the out of plane displacement component. So, this B matrix signifies that even if there is no in plane displacement component, suppose in plane displacement component is 0, even then just out of plane displacement components, because of this coupling, can give rise to something n. Or in other words, if I apply pure in plane load, then also some kappa which contains out of plane displacement can be induced. Similarly, here m, if I do look at this relation, m is equal to b into epsilon 0 plus d. This also means that if I just apply pure bending, I can get in plane displacement components and in plane strains as well. So, A is our in plane stiffness, D is our bending stiffness, and B is coupling stiffness. So, A signifies in plane stiffness, B signifies coupling stiffness, we can say, and D signifies bending stiffness. And also we can see that this A is a 3 by 3 matrix. So, it has components like AXX, AXY, ASX, AXS. So, a quantity like AXS, it couples the normal force components with the shear strain. Similarly, I can have DXS also, and that couples bending moment with the twisting moment. So, we can get rid of some of the couplings by proper lamination sequencing. Sometimes the couplings are desirable, sometimes they are non-desirable. So, let us look into a symmetric laminate. So, a symmetric laminate, as the name suggests, has the ply orientation symmetrically placed. So, again let us imagine that we have something like this. So, layer 1, this is layer n, this is layer 2, this is layer n minus 1, and we can call a generic layer k, and a symmetrically opposite layer is k prime. So, this is our mid plane z is equal to 0. So, with respect to this mid plane, this ply, I mean this layer and this layer symmetrically placed. Similarly, this layer and this layer are symmetrically placed, this layer and this layer at the symmetrical location, this layer and this layer at the symmetrical location. Now, if at these locations, for example, at layer k and at layer k prime, if the orientation is, if the ply orientation is same, we call it a symmetric laminate. Similarly, so if at layer 1 and at layer n, if the ply orientation is same, if the layer 2 and layer, if at layer 2 and at layer n minus 1, if the ply orientation is same, and accordingly for any k, if the ply orientation at k and k prime location they are same, we call it a symmetric laminate. So, orientation and ply thickness both have to be same. So, in all our analysis we are assuming that our ply thickness is all same, all the plies have same thickness. So, for example, a laminate like this, which is, so generally we show a lamination sequence in this form theta 1. So, suppose suppose we consider this sequence where I have 1, 2, 3, 4, 5, 6, 7, 8 number of plies. So, suppose our laminate sequencing is this theta 1, theta 2, theta 3, theta 4, then we have suppose theta 5, theta 6, theta 7, theta 8. So, the lamination sequence is shown in this form theta 3, theta 4, theta 5, theta 6, theta 7, theta. Theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, theta 7, theta 8. So, this is how the lamination sequence is shown. Now, suppose in our case theta 5 it is symmetric. If it is symmetric, then we have theta 5 is equal to theta 4, theta 6 is equal to theta 3, theta 7 is equal to theta 2, theta 8 is equal to theta 1. So, in this case we can show it as theta 1, theta 2, theta 3, theta 4 and S. S means it is symmetric. So, it repeats itself in a symmetric fashion. So, for a symmetric laminate it can be shown that the B matrix is always 0. For a symmetric laminate, always. It can be proved easily also. So, we know that the property of the q at kth ply and q at k prime ply, they are same. So, if we add the contribution to the B matrix from this ply and if I add the contribution to the B matrix from this ply, they are just opposite of each other and on being added they become 0. So, that way if we do it for all the plies, the entire B matrix comes to be 0. So, in a symmetric laminate there is no coupling between the in plane and the out of plane components. Now, there is something called a balanced laminate. In a balanced laminate is something where we have number of plies with theta 1 orientation is same as number of, or theta I orientation is same as number of plies with minus theta I orientation. So, a laminate like this, suppose 30 degree, 40 degree, minus 30 degree, minus 40 degree. Generally, we do not show the degree sign while writing the lamination sequence, we can get rid of it also, it is understood. So, that is a balanced laminate, because if I have a 40, I have 1 minus 40, if I have 30, I have 1 minus 30. Similarly, if I have something like 30, 45, minus 45, 45, minus 45, minus 30, it is also balanced, because I have 130, I have 1 minus 30, I have 2 45s and I have 2 minus 45s. So, it is balanced. So, these are for angle ply laminates. Angle ply means where the angle of orientation is neither 0 nor 90, it is a angle ply laminate, and if the orientation of ply is either 0 or 90, we call it a cross ply laminate. Now, in a cross ply laminate 0 and 90 are supposed to be opposite. So, 90 0 90 0, this is also balanced, because as we said 90 and 0 are opposite in a cross ply laminate. So, if I have a 90, I have a 0, if I have two 90s, I have two zeros also. So, they are all balanced. So, these are all balanced laminates. Whereas, something like this, if I have 30 minus 30 minus 30, 90 90, this is not balanced, because I have 130. So, I have 1 minus 30, that is okay, but I have 190, for this I should have a 0, but that is not there, I have another 90. So, it is not balanced. Now, again this balanced laminate can be of different types. So, it can be symmetric and balanced. Okay, so, before going, it can be symmetric. So, symmetric means which is symmetric as well as balanced. So, for example, plus minus 31, plus minus 32 symmetric, that is a balanced laminate. An example can be 30 minus 30, 45 minus 45 symmetric. So, it is a symmetric as well as balanced. It can be antisymmetric. Antisymmetric means plus 31 plus 32, sorry, plus theta 1 plus theta 2 minus theta 1 minus theta 2 minus theta 1, that is antisymmetric, because with respect to mid plane, if I look at two locations which are symmetrically located, the orientations are just opposite. So, if I have theta 2 here, I have theta minus theta 1 here, if I have theta 1 here, I have minus theta 1 here. So, an example is 30, 30, 30, let us call it 30s and 30, 45 maybe minus 45 minus 30. So, that is antisymmetric, and there can be asymmetric. So, it is neither symmetric nor antisymmetric. So, it can be suppose theta 1 minus theta 2 minus theta 1 minus theta 2. So, it is neither symmetric nor antisymmetric. If we look at it with respect to the mid plane, we can see that. So, maybe 30, okay, it is plus, I cannot have 2 minus. So, it is plus 30, 45 minus 45 minus 30. So, it is asymmetric. Now, for any balanced laminate, now AXS is equal to AYS is equal to 0 for any balanced laminate, it can be proved. And then if the laminate is antisymmetric, then we have dxy is equal to dys is equal to 0 for any antisymmetric laminate. So, in a antisymmetric laminate, there is no coupling between the bending and the twisting components. So, sometimes this coupling is desirable, sometimes this coupling is not desirable, and accordingly we can design our laminates. So, that is what gives us tremendous design flexibility when we use a composite material. And then if the laminate is cross ply and antisymmetric, like a laminate 090 090, then the B matrix looks like this. So, Bxx and Bxx and Byy are opposite of each other, and rest of the quantities are 0 for antisymmetric cross ply laminate. And then we have 0 0 Bxs, 0 0 Bys and Bxs Bys 0 for antisymmetric angle ply laminate. So, we know the transformation, the relation for each plies for theta, and we know that in a laminate where I have balanced, there are thetas and minus thetas. So, accordingly we can look at the transformation, and after looking at the lamination sequence, we can just these quantities, whether they are 0 or not, it can be easily shown. Now, we will talk about another type of laminate. And that is called quasi isotropic laminate. So, in a quasi isotropic laminate, adjacent laminates are oriented at pi by n, where n is the number of laminates. An example can be a laminate which has orientation 60, minus 60, 0 and is symmetric. Now, in these laminates, the behavior of A is of isotropic nature, but B and D matrices are not. So, if we look at the A matrix, it looks like this. So, this is how a matrix of a quasi isotropic laminate looks like, and we have A x x is equal to A y y here. So, this is more of a isotropic behavior. So, A matrix is isotropic, but B and D are not. So, we saw how to relate the stress resultants with the strain components, and then we defined matrices like A, B and D matrix, and we saw that depending on the lamination sequence, some of the couplings are there, some of the couplings are not there, and we get some special relations also in some cases, like here we have A x x is equal to A y y and so on. So, these are quite useful observations, and they are quite useful in designing a composite laminate. So, with that I would conclude this lecture here. Thank you.